Welcome to part 2 of our series on risk analysis. For over 40 years, ITEM software has been the acknowledged world leader in reliability, safety, and risk assessment software, providing the global engineering community with precision tools to navigate complex RAMs evaluations. In our first video, we defined the fundamental nature of risk. Now, we are shifting our focus to the methodologies used to solve it. In this session, we will distinguish between traditional and dynamic methodologies and explore how the ITEM Toolkit and ITEM QRS platforms allow you to organize and represent risk scenarios with industry-standard accuracy. Whether you are performing a top-down or bottom-up analysis, our goal is to show you how to find the most effective path to a safe and reliable system. In risk assessment, there are several methodologies available to help analysts identify hazards, model failure scenarios, and estimate the likelihood of undesired outcomes. These methodologies can generally be grouped into two broad categories: traditional methodologies and dynamic methodologies. Traditional methodologies include techniques such as fault tree analysis, event sequence diagrams, failure mode, effects, and criticality analysis, and other structured engineering approaches. These methods rely on the analyst to define possible system failures, model how those failures propagate, and evaluate their probability and consequences. They are widely used because they provide a clear, traceable, and logical representation of risk scenarios. Dynamic methodologies, such as Monte Carlo simulation, take a different approach. Instead of manually constructing every scenario, they use executable or simulation-based models to represent system behavior over time. This can be useful when timing, interactions, or system evolution are important. In this part of the series, we will focus mainly on the traditional methodologies because they form the foundation for many practical reliability, safety, and risk assessments, and they are directly supported by tools such as ITEM Toolkit and ITEM QRS. To understand why these methods are the foundation, we must first define what we mean by a traditional methodology. Simply put, it is a collection of established techniques used to identify and assess the probability of scenarios that could lead to an undesired system state. These methodologies rely on the analyst to systematically assess potential failures and build the logic that governs the system's behavior. The quality of the analysis result is often directly dependent on the expertise and thoroughness of the analyst. Within traditional risk assessment, we generally approach a system through two different logical paths: the inductive method and the deductive method. Inductive method is a bottom-up approach. It involves reasoning from individual cases, such as the failure of a specific component, to a general conclusion about how that failure affects the entire system. Common tools for this type of analysis include failure mode, effects, and criticality analysis, reliability block diagrams, and event sequence diagrams. Conversely, the deductive method is a top-down approach. It constitutes reasoning from the general to the specific. In a deductive analysis, we postulate that the system itself has failed in a specific way, which we call the top event, and then work backward to identify all the combinations of component behaviors that could contribute to that failure. The industry standard tool for this method is the fault tree analysis. Understanding these two paths is essential, as most robust safety cases require a combination of both inductive and deductive viewpoints to be truly comprehensive. After choosing the appropriate methodology, the next step is to implement it in a structured modeling environment. ITEM Toolkit provides an integrated environment that supports both inductive and deductive modules in a single project. Toolkit is designed for accuracy and ease of use, offering a consistent format for all your analyses. This standardized interface ensures a natural learning carry-over between modules, allowing you to optimize designs and reduce liability efficiently. While ITEM Toolkit provides specialized modules for individual analyses, ITEM QRS offers a uniquely integrated environment for full-scale probabilistic risk assessment. It provides a seamless combination of inductive and deductive methods. At the high level, it utilizes the inductive method event sequence diagrams to describe possible risk scenarios following a system perturbation or initiating event. Each pivotal event within those sequences is then further detailed using deductive fault tree models. This hybrid approach allows you to answer critical questions regarding how large your risks are, what the major contributors are, and how changes to your system affect overall safety. While we have focused on traditional logic, it is important to briefly mention dynamic methodologies. These represent a set of techniques where executable models simulate the physical processes and behaviors of a system over time. In a dynamic approach, event sequences are generated automatically by controlling stochastic events within the model, often through probabilistic simulation or Monte Carlo techniques. This can be useful for highly complex, hybrid systems where the timing of interactions between hardware, software, and human components is critical. In this series, we will mainly focus on traditional risk assessment methodologies because they provide the foundation for the item software tools and examples we will demonstrate. But understanding the distinction between traditional and dynamic approaches helps us see the broader landscape of risk assessment method. This concludes our overview of risk assessment methodologies. We have distinguished between traditional and dynamic approaches, and within traditional methods, between inductive and deductive reasoning. In our next video, we will step away from the software to introduce a comprehensive real-world case study, identifying the hazards and scenarios we want to capture before the modeling begins. Thank you for watching, and we'll see you in Part 3.